Okay, chances are you probably haven't done anything yet about capacitors in physics, so this should hopefully get you started. Um, in its simplest form, a capacitor, a simple capacitor, is just made of two parallel conducting plates separated by an air gap. So it could be two bits of aluminium or something like that, which have a gap in between them so that current can't flow between the gap. And that's as simple as that. If you've got two bits of metal near each other, you've got yourself a capacitor. Well, what can you do with it? One thing you can do with a capacitor is connect it up in a circuit. So if you connect each of your plates to different sides of a power supply, like a battery or something like that, then current starts to flow in the circuit. So here we've got the negative side of the battery here, positive side here. This is going to push electrons around this way and pull electrons off this side, so that you get electrons starting to build up on one of the plates, and left behind on the other plate you will have positive charge because electrons have left. So what happens with these plates is that they start building up an equal and opposite charge on either side. Now that continues until the voltage across the capacitor equals the voltage of the supply. So there's a voltage across your cell, 1.5 volts, something like that. Charge will continue to build up until the voltage across the capacitor equals that. And when that happens, there's going to be a certain charge, let's call it minus Q, built up on this plate, and an equal and opposite charge plus Q built up on that plate. The charges on each plate have to be equal and opposite because they arise from electrons moving from one plate to the other, and electrons aren't disappearing off anywhere in the circuit. So essentially, the capacitor allows you to store separated charge. The overall charge on the whole capacitor itself is neutral, because the charges on each plate are equal and opposite, but it stores that charge in a separated form. So one charge on one plate is positive and the other is negative. So that's a capacitor. What are they used for? Well, they can store charge that is separated, and one of the things that's useful about capacitors is that they can be charged up very quickly, and they can also discharge very quickly as well, which is quite handy for certain applications. So if you need a power source that can supply a lot of current and supply it very quickly, one option for that is a capacitor. So let's go back to this with all our electrons built up on here and all our positive charges remaining over here. Obviously these electrons want to get back around there. So if you then discharge your capacitor across something, like a bulb or whatever, there's very little resistance in the capacitor because it's just made of metal plates and then wires attached to it. So it can supply a very high current. So they're quite useful in things like camera flashes, where the camera flash needs to supply a very brief, short burst of energy. In that instance, it's not a normal incandescent bulb in a camera flash, but nonetheless, the idea is that they can be used to deliver current very rapidly. There's loads of other uses for capacitors too, but we won't really be able to talk much about those until we've done a bit more about capacitors in circuits. So, moving onwards, there's a formula for capacitance, the capacitance of a capacitor, and it's quite straightforward. The capacitance C is the amount of charge Q stored per unit voltage V. Okay, so if we look at our a capacitor, like this one here, the capacitance is the charge per unit voltage. How much charge gets built up on these plates per unit voltage here applied. The more charge that gets built up for the same voltage, the greater the capacitance, the greater its capacity to store charge. We better chuck in the units quickly. Charge Q is measured in coulombs. Voltage V is measured in volts. So capacitance could be measured in coulombs per volt. That has an equivalent unit, the farad, capital F. That's the equivalent unit, and that's the one we're going to be using. So we can quickly just use this to calculate the capacitance of two different capacitors. You'll notice that one is bigger than the other. Let me just move down a bit. So C equals Q over V. So for this capacitor here, the charge stored on the plates is 1 coulomb divided by the voltage, and we'll assume that this is charged up, so the voltage across the capacitor will be 4 volts, so that's going to be 0.25 farads. Simple. This one here, C equals Q over V, which equals now 2 coulombs stored on the plates divided by 4 volts, which is 0.5 farads. So you'll see that by having larger plates, this capacitor has a greater capacitance than this one. Okay, that kind of stands to reason. There's more space to store charge, so this one's got a greater capacitance. We can take this a bit further to find out what other factors affect capacitance as well. So if we have a look at our capacitor, when it gets charged up, obviously an electric field exists between these plates because it's two charged plates, and we know what that looks like if we have an electric field between two charged plates. We've done that before. Now there are two ways of expressing the electric field that we know about. One we just talked about recently, which is the electric field strength on the surface of a charged conductor is related to the surface charge density. That's the charge per unit area with this proportionality constant. The other way that you know also is the electric field strength is the potential gradient. So it's the potential difference V divided by the distance between the two plates, D. So if I label that in, whoops, that's D, the distance between the two plates. A would be the area of each of the conducting plates. So with these two formulae we can obviously equate them, and we can do that by just equating the fact that E appears on both of them. We can therefore equate the right hand side of each equation and say that Q on E naught A is equal to V over D. Now if we do a quick rearrangement of this, we can get to the formula for capacitance. So if we cross multiply and get that up there and that up there, then you'd have QD equals V E naught A, and then we'll do a shifty bit of division because we want Q over V, so now we'll divide both sides. Here we go, to get Q over V equals E naught over E naught A over D. If you were happy to just flip that all in one step, then that's even better. So we've got to this stage here where Q on V equals E naught A over D. Well, Q over V, charge per unit voltage, that is nothing other than the capacitance. So it turns out that the capacitance, the formula for capacitance for our parallel plate capacitor, is E naught A on D. Now this is quite intuitive. If we double the area of the capacitor, we double the capacitance, but also this shows you that if you bring the plates closer together, if you decrease D, that also increases the capacitance as well. So there's two ways of varying the capacitance, and it turns out there's another as well, which isn't on our syllabus, either by changing the area or by changing the separation of the plates. So I haven't actually mentioned it yet, but the symbol for a capacitor is this, pretty straightforward. Often it's not an air gap in between because it would be impractical, and it's also better if you put something else in between it. So usually there's some sort of insulator in between, which is also called a dielectric, So it's rare that you actually have an air gap in between. Usually it's something else. Also, often when they're made, you'll have two thin metal sheets with an insulator between them, and then to make it take up less space, they get rolled up, kind of like a sausage roll. So they get rolled up, which is why some capacitors are cylindrical. This capacitor's a cylindrical shape. It's rare to have large capacitances measured in farads, whole farads. Often they're really small. Millifarads, microfarads, nanofarads, picofarads. Be prepared to deal with any of those. You come across very small capacitances. Having said that, these days ultra capacitors are becoming much more common. And if you go on eBay, you can find you know, a 350 farad capacitor for not a lot of money, less than 50 quid probably. That would have been unheard of 20 years ago. So there are now capacitors available with huge capacitances for not that much money. The only other thing to note is polarity. Some capacitors have to be connected the correct way round. Not a basic parallel plate capacitor just made of, you know, two plates and an air gap, but certain capacitors need to be connected the right way round, otherwise they explode. So be careful with that in case we do use any of those electrolytic capacitors. Right, I think that's your lot. I've just got a couple of quick examples which are worth having a go at and thinking through. So, number one, a capacitor is charged to a voltage of 1.5 volts and it stores a charge of plus or minus 6 times 10 to the minus 7 coulombs on each plate. What is its capacitance? And ideally I'd like it in one of these nice units like millifarads or microfarads or whatever. 2, how does the capacitance of capacitor 1 compare with capacitor 2? So this one, the separation is twice as much, and the dimension of the side of the square is also twice as much. So how will the capacitance compare for these two capacitors? Have a really good think about that. So pause the video now. Alright, excellent. Hopefully you've given that a bit of thought. Number one's pretty straightforward. So capacitance is charge per unit voltage, Q over V, and we know that that's 6 times 10 to the minus 7 coulombs on 1.5 volts, and 1.5 goes into 6 4 times, so that's going to be 4 times 10 to the minus 7 farads. Now what can we do to make that into a nice one? Well, we could multiply the first bit by 100 to make that 400, and then divide the second bit by 100 to make that 10 to the minus 9 farads, and 10 to the minus 9 farads is nanofarads, so that would be 400 nanofarads. Equivalently 0.4 microfarads if you went that way. Question 2, how does capacitor 1 compare with capacitor 2? Well, we need to think about that formula. C equals E naught A on D. Now let's say this one's got area x squared. This one's going to have area 2x squared, which is 4x squared, if you see what I mean. So it's got 4 times the area, and it's only got 2 times the distance between. So if this is times by 4 and this is times by 2, the overall effect is to multiply the capacitance by 2. So 2 will have twice the capacitance of 1. Excellent. If you just said that capacitor 2 will have a greater capacitance than capacitor 1. Well, I want you to think about it a bit more carefully than that. So make sure you can follow through this ratio stuff. Right, that's your lot for capacitors. Hopefully next lesson we will try and make an actual capacitor and see if it works.